So in the case of image textures, that's what we do. But sometimes we want to apply bump mapping for procedural textures as well. Okay, so procedural textures, or in particular volume textures, such as the Perlin noise. You know, Perlin noise is defined at every point in the 3D volume. Okay, we can give an XYZ value and compute the corresponding noise value. So there is no really image. And actually Perlin noise is not parameterized with respect to U and V. Okay, so how do we deal with that case? How do we apply bump mapping if the bump source is a Perlin noise source? Now, to understand that, we need to think about the meaning of these vectors. Okay, so du and dv. So what do they? These are actual scalar values in the case of images. So what does it represent? It represents the rate of change, the rate of change of the height map along u and v directions. Okay, so another way of representing rate of change in computer graphics, or in image processing, or in whenever we deal with vectoral quantities, is using gradients. So a gradient of a surface represents the direction and the magnitude of a rate of change on the surface. So let's say we have a surface like that. Okay, so at every point on the surface, let's say a 3D surface. Okay, so at every point on the surface P, a gradient is a vector. Okay, the gradient vector is a vector that points along the greatest rate of change on the surface. So gradient is normal to the surface. Okay, so gradient is normal to the surface. A gradient vector is normal to the surface. Now, how do we make use of that? Now, the gradient represents the rate of change. Okay, so what we do in the case of Perlin noise is we compute the gradient of the Perlin noise. Okay, so gradient of Perlin noise. Now, how can we compute it? Remember, again, it represents the rate of change. So how does this surface value change? How does the surface value changes as we go by minimal, tiny amounts in each direction? Okay, so the gradient of the Perlin noise is defined as this vector. It is the delta, let's call it the Perlin, let's give it a name to the function. Okay, so let's call it, I don't know, let's call it h. Okay, delta x, delta h, delta y, delta h, delta z. So the h here represents the Perlin noise function. Okay, so h is actually like Perlin noise is h xyz is equal to noise value at xyz. So we have learned how to compute the Perlin noise in our previous lecture. So the gradient of the Perlin noise can be computed by tiny increments, by recomputing the noise value at differential increments of the noise function and along each direction. Now, from a practical point of view, this can be computed as follows. The gradient of the Perlin noise. Okay, so h is the Perlin noise function. Okay, so the gradient can be computed, the x component of the gradient can be computed as h x plus epsilon yz minus h x yz divided by epsilon. So this is the x component. Okay, so we have made a tiny change along the x direction and then subtracted it from the original value and we divide it by the epsilon. Okay, so what is xyz? Xyz is our intersection point. So our ray has intersected at this surface, at the, let's say, a sphere or a triangle at xyz. Okay, now for the y component we simply say x y plus epsilon z minus h xy z divided by epsilon, and h x y z plus epsilon minus h x y z divided by epsilon. Okay, so this epsilon, what should it be? It's a small value. You can of course use different numbers for this. So let's say as long as you use a small value, it should give you sufficiently good results. For example, E can be 10 to the power of minus 3. Okay, basically a small value. It can be a smaller value or it can be a slightly larger value. There is no like a single number that will that can be said to be the best number. Okay, if you make it too small, like you are going to run into floating point precision issues. Okay, if you make it too large, it's not going to represent the change sufficiently. Okay, so something like that should produce good results.